Okay, I'm assuming this will probably be a short meeting, especially since we just lectured on the material today. But if you have any questions, I can answer them. So I do have some clicker questions I can ask from chapter 34. So we can do some clicker questions. Okay? And some of these are quick. So let me put up the first clicker question. And let me launch it. Okay, so assume the amplitude of the electric field in a plane electromagnetic is E1, and the amplitude of the magnetic field is B1. Oops, I have a notation problem, sorry. The source of the wave is then adjusted so that the amplitude of the electric field is doubled. What happens to the amplitude of the magnetic field? That should say B1, not BM. And also what happens to the intensity of the wave? If I double the amplitude electric field, what happens to the amplitude of the magnetic field and total intensity of the wave? That's the question. Okay, I have about 2 more people need to respond. All right, I got all responses. Let me show the results. You all see the results? Okay. So let me go to the board. And really, a lot of the stuff in this chapter is equation driven. So from Maxwell's equations, from solving Maxwell's equations, the ratio of the electric field, the magnitude of the electric field to the electric field to the magnitude of the electric field is C. So the ratio of E over B is C. Okay, the ratio of electric field magnitude to the magnetic field magnitude is C. So that means if I double this, I have to double that. So that eliminates C and D so far. Now, what does the intensity depend on? The intensity is equal to S average, which is equal to U total, small u, times the speed of light. And in fact, this is the average value, which can be written a number of ways, because it can be written as E times B over 2 mu naught. And these are the magnitudes. It can be written as B sub m squared over 2 mu naught. Oh, there should be a C here. But either way, you can see that if you double one and you double the other, that's got to go up by a factor of 4. If you double this, I is going to go up by a factor of 4. So that means that the answer to this one was B. Okay. So let me ask you another question, because I have 3 more. These should go quick because there's only 2 responses. So you have a wire with a bulb attached to it, and you have a large electromagnetic wave approaching the wire. The question is, when the wave interacts with the wire, will it cause the light bulb to go on? And let's assume the electromagnetic wave is sufficiently big to make the light bulb go on. So it's either yes or no. So in this picture, the electromagnetic field is oscillating vertically, and the magnetic field is oscillating in the horizontal plane. Okay, everyone's responded, so let me end the poll. Share the results. Okay, so let me go to the board. Let me stop sharing the results. Okay, I have a wire in the vertical position, because the wire has a lot of free electrons in there, right? Okay. Now let's say we have something here that completes the circuit, whatever. So we have electromagnetic wave. The electric field oscillates this way. So the electric field oscillating this way, and we have a wire which has a bunch of free electrons in it. When the electrons in here interact with the electromagnetic field, what's going to happen? There's going to be an up and down force on the electrons. And the electrons have a path to move through, right? They can move up and down. Okay? The electrons can move up and down. And so basically, I'm producing a current. Of course, if the field's big enough, that's why I said assume the field is sufficiently large. If the field's big enough, I'm going to be able to produce a large enough current to make this light go on. So the answer is yes. By the way, what would you call this thing? Let's say I have 2 wires like this. And maybe I can actually, these go way out far, but what do you call this thing? Is there a name for this? Something to pick up? Yeah, it's an antenna. Okay, that's an antenna. It's a dipole antenna. Okay, and there's a lot of physics involved with the dipole antenna, which we can't really go through. Okay, because to be precise, the equations are pretty complicated. All right, now let's take a look at this case. The wire is horizontal and the electric field is in the vertical plane. Just need one more person to respond. It looks like people are changing their minds. Okay. All right, so let me end the poll. I got everybody response. Let me share the results. Okay. Oops, sorry, I didn't magnify the slide. Okay, let me stop sharing. If the wire is like this, the electric field oscillates up and down like this, and the bulb is over here out of the plane. The electric field all it can do is make the electrons move up and down. In order for the electrons to be able to move through the wire, the electric field has to be this way. In fact, the electric field would have to be in the direction of the magnetic field that you see there. If you swap, in the figure, if you swap the electric and magnetic fields, then yeah, you would get the light bulb to go on. But in this orientation, it's impossible. You can't get the electrons to move. The electrons would move vertically, but the rod's horizontal. Okay? So when you're using an antenna, it's got to be in the right orientation. Otherwise, you're not going to be able to pick up anything. Okay, one last question. What about this case? Let me make the slide bigger. Think about how you can get the electrons to move. Well, you got a 50-50 split here. All right, let me end the poll. Let me share the results. So basically it's a 50-50 split in this one. Okay. So again, let's take a look. I'm going to have the electromagnetic wave drawn up there. If the wire's like this, and the electric field's this way, then the electric field can only make the charges move up and down. They can't make it move along this direction. Okay? Electric field can only make the charges move up and down. I would need an electric field that oscillates like this. Okay? This oscillation just tells you how large the magnetic field is. If you look at the picture that you see for the electric field, you see a bunch of arrows drawn. Those arrows represent the electric field at that instant in time. But the direction's still up or down. So that means that if I have a wire that's oriented like this, all this field can do is make the charge move up and down. Of course, if this is a really thin wire, then you're not going to get any charge moving horizontally. So the answer is no to that one. Okay, do you folks have any questions? Any general questions? Because this is our last meeting. We're not meeting next week. Okay, we're not going to meet next week since it'll be after the exam. Any questions in general? No. You have one, Asher? What's your question? The lab equipment? Okay. What about the lab equipment? I'm going to send an email with the lab equipment. Okay, Asher? Yeah, somebody asked me earlier, and so I'm going to send a list. Each lab actually individually has the list of what you keep and what you have to give back. But I'll send you the list, the overall list. Yeah, I got to change that. That's a mistake. So what happened was, again, when we had the problem with the textbook, I created a new course. And so the course started later. And so what it does is it takes the homework assignment from the previous semesters, because I just copied the homework assignment from previous semesters, and it just extrapolates the date. So I extrapolated the date way too far out. I'm going to change the date. I'm also I have to change the number of problems. I got to limit it to like 5. Okay, so the last homework assignment will only have 5 problems on it, which doesn't make me happy, but it is what it is. Okay. So that'll be fixed. So just focus on homework 12 for now. You should be able to get homework 12 out quickly because a lot of the problems are just plug and chug, except maybe the first 2 problems. The first 2 problems are the displacement current, and there's a problem really that belongs in chapter 31. I'm not sure why it's here, but it's a good review problem anyway. Okay, I will send you, yeah, there's also one I owe you about the complex plane stuff. I'll send that too. Okay. All right, any other questions? So you do have quite a few things to get through. You got to get through chapter 34 homework in that lab. You want to get started on the lab right away. Yeah, I'm going to make the last web assignment due Tuesday. You're right, Andrew. And I'm only going to make it 5 problems. With my other group, I have 3 hours to lecture on relativity. So, in fact, with the last group, I have 3 hours plus the lab next week to lecture on relativity. So I can get through a lot of stuff on relativity with the other group. So if anybody's interested in going to a 3-hour lecture on Friday, I can give you the link. If you're like Patrick, you've been interested in more relativity stuff, so I can give you the link if you want to. Okay, I guess that's it then. So won't see you till Monday. We'll talk a little bit about relativity. And that'll be it. So unfortunately, we didn't get through enough material, but that's okay. this is a weird semester. Yeah, I'll keep the YouTube videos will always stay there. I mean, the intent is not to use them like every semester, but if you know if people can look them up, you know, part of the problem is that the way they're not designed to be a regular lecture. Those YouTube videos is really only for us folks, because I get questions asked during the lecture, and I'm walking to the screen a lot. But for you guys, yeah, they'll be there for a long time. And I have stuff from last semester too over there. Okay, we'll talk to you. Yeah, have a good weekend. I'll see you next week.